continue. We are just going to WinPad 2. Yes, this diagram I showed you last time, I think so. Yes, this one we have all done, is it?
Yeah.
Yes. This we have done. This one we have not done. Go one back. So yeah. This one we have not done, that's the basalt tetrahedron. You know by now where basalts are formed, yeah? You know this from ES203. I mean, most of the basalts, they are formed at the middle ocean ridges, yeah? So, but then you can also form basalts, or that are the different basalts. There you are forming andesites and sociolites and so on, that you can then form at subduction zones. Or you can form basalts also on the ocean island basalts. You have there also basalts, for example, if we are talking about an hotspot. So, and on the continental side, of course, there you have usually no basalts. So, and I showed you 2 weeks ago maybe something like this, the chemical composition for basalt, and compare the chemical composition from the basalt with those from the continental crust. So, and you know by now as well that basalt is an exclusive rock, and the counterpart from a typical basalt, that is gabbro. And gabbros you can find here, and if you have been at, you know, because Lenoir did not go with you to this outcrop, yeah, that is a big mess, because there you would now know where you can find here basalt. But it depends still where we are going for the ES203 field trip. Maybe we can do it, arrange it like last year with the ES303 and the ES301, that we are going to Vanuatu instead of Koro, and then we can visit before Yahuna Creek, yeah? That you have seen these tonalites there and these basalts there. Anyway, the basalts can be subdivided, and therefore we are using this tetrahedron, again with this nice projector, yeah, that is now working for more than a half year.
The next week the projector is already here.
They have it now already here, now they need another 6 months to install it, yeah? So, and now we have here the main components of such a basalt. We have here at the top, we have clinopyroxene. You know by now what a clinopyroxene is, and you know also the chemistry of the clinopyroxene. And Neil has done with you the amphiboles as well, yeah? And you have also done the exchanges, yeah? Okay, great. So then you should check, especially from the pyroxenes and from the micas, all these exchanges, because that is a nice question for the examination, as well as for the test. I saw I will upload the test one last week, but I would like to include also the things what we are doing this week. But anyway, the test is a homework, and you can then just hand in the test on that Thursday after the midterm break, yeah? So that should give you enough time, yeah? And I will upload the test by tomorrow, yeah? You can just download it on Moodle. There are some questions, and you have to answer this question very carefully just by using your script, yeah? It should be not a problem. So now we have here the basalt tetrahedron. At the top we have the clinopyroxene. Here we have the naphthalene, yeah? Here we have the olivine, we have the orthopyroxene, and here we have the quartz. So, and if you are looking at these minerals inside, then you know from classes before, and also you should know this from the practical yesterday and the week before, because Neil did again with you these melt diagrams, yeah? Yes. And there you have done the peritectic point, the eutectic point, and a thermal boundary, that is the distecticum, yeah?
That is the one with the eutectic.
What?
The eutectic.
Yes. So, but you should know from the classes before and from the class today and from the practicals that quartz never occurs with olivine, yeah? Because quartz is always in silica saturated rocks, yeah, that means where you have quartz crystals inside, and olivine is always occurring in silica undersaturated rocks, yeah? Because if olivine comes with a little bit silica in contact, that is at the peritectic point. Yeah, you know the peritectic point by now. You must just check the diagrams from before. And the peritectic point, I'm writing again here. The peritectic point that is, at this case, Mg2SiO4 plus SiO2, then you are forming Mg2SiO6, Si2O6, yeah? So, and there, for thermodynamically, it is not possible that you can have olivine and silica together because you are forming them immediately here the enstatite, yeah? That is just, this here is just an unstable condition, and then you are going immediately from unstable condition to a stable condition and forming the autopyroxene here, yeah? Olivine plus quartz is autopyroxene. You can just use your hand tool. You have now done also this a lot, yeah? Then you have olivine plus quartz is enstatite, yeah? Finish. So here on this side we have the nepheline, and you know the nepheline, that is a fluid mineral, yeah? And fluid minerals, if you are checking your course outlines, then you can see that the fluid minerals in the QAPF diagram is always plotting beneath, yeah? At the top you have quartz, you have this geometry, and the nepheline is plotting on the upper part, and that means the nepheline also occurs never together with quartz. So because nepheline also occurs only in very silica undersaturated rocks. So and then we have here at the point between quartz and nepheline, we have the mineral plagioclase, yeah? So the plagioclase can occur in all type of these rocks. You can also make your hand tool now again. Quartz plus nepheline gives you plagioclase, yeah? So if you are just writing down the reaction, it's totally easy, or at least I think it's easy. Then you have SiO2. Then you are making here the plagioclase. We are using here an albite, yeah? Yes. Na, Si3O8. So, and then we have the nepheline, that is the albite. That is the quartz. So, and then we make here the nepheline. So, and that is NaAlSi2O6. So, and finish is the nepheline, and that's happened here at this point. Yeah? So, but now we have here the plane of silica saturation, and that is here. So that means we have here a basalt where we have quartz inside, and this basalt contains then of the minerals clinopyroxene, plagioclase, autopyroxene, and quartz, yeah? So, and we are calling these basalts colloids, yeah? So in these colloids you will not form at the middle ocean ridges, because at the middle ocean ridges you are forming the olivine-bearing basalts. So then we have the next plane here, and that is the plane with the minerals clinopyroxene, olivine, autopyroxene, and plagioclase. So, and these are these typical olivine-bearing tolloids. So, and then we have here the plane of silica under saturation, yeah? That is this plane here, then you can have also a basalt containing of olivine, plagioclase and clinopyroxene. And here you have the totally silica undersaturated basalt, and that is then contains the methylene, olivine, plagioclase and clinopyroxene, yeah? So for you as an as an ES203 student, you should just be aware of it, that we have silica saturated basalts and silica undersaturated, yeah? So in these basalts, which you can find here always on all the Fijian islands, yeah, they are all silica undersaturated. There is not only silica saturated basalt, the only silica saturated rock which you have here, these are the tonalites and the diorites. So next slide. So now we have another very funny diagram. We have here the Al2 concentration of melt and potassium concentration, yeah? So and here we have now the melt as it occurs at the middle ocean ridges, yeah? You have the melt as it occurs at the middle ocean ridges, and that is a melt which was produced by decompressing, yeah? You know this by now? So where is this cleaner?
There on the board.
On the board. A melt, how it occurs at the middle ocean ridges. So, and if I'm asking such a thing, then you can just make again a diagram how it looks like roughly. Here we have the middle ocean ridge, and here we are going towards two continents, for example, yeah? Here we have the oceanic crust. So, and then we are making the water level, yeah, that is always important that one know where is the top and where is the bottom. So that is now a little bit a stormy sea. Then we make here the continental crust again. No, not in blue, I have already made the water in blue. Then we make the continental crust maybe in black. So, continental crust CC, not for calcite. So, and now we are making here a melt in red because that's hot. So and now we are producing here melt, yeah, you know this by now at the middle ocean ridge. So and then if we are producing here melt, and I mean this melt comes from somewhere, yeah, from below, and then we are making here the typical basalt as we can find it here in the, or as it produced at the middle ocean ridge, but then we have a residue. So, and that is very important because below the oceanic crust you have the mantle slab, yeah? So in the mantle slab I showed you pictures consist of peridotites. And these peridotites are dunites, harzburgites and lersonites. So in these dunites, harzburgite and lersonites, they have also to be formed somewhere at the middle ocean ridge, yeah? So if we are just making it more detailed here, Then we have here the oceanic crust just in this part, yeah? So here that's the oceanic crust, yeah? So that is the oceanic crust. So and that we are calling then what happens there, partial melting. So and then you are forming at the top, you are forming the oceanic crust, the more basalt, but then you have fractionation processes in the magma chamber there. So and then you have fractionation process in the magma chamber, and which minerals will become removed. You should know this by now. Which minerals becomes very early removed from such a melt. At high temperatures we are removing at first olivines. Then we are removing autopyroxenes, we are removing some plagioclase, and we are removing, maybe it depends on the pressure, we can also form or remove them garnets, yeah? So and therefore we have here the more basalt. So that is then formed here. Here we are forming the more basalt, and here due to partial melting, we are forming below a garnet lersolite, then we have olivine nodules, and then we have Harzburgite, yeah? So in this we are calling the residual melt. Residual melt. In some books they are writing this as a restite. So and if you are looking at this garnet lersolite nodules from Coro, you have showed them one, yeah, a few weeks ago. Then the question to answer is, are these garnet lersolites a residual or a restite from the andesites and the basalts which they have brought up? Or are these andesites and these andesites and basalts representing a melt which has picked up them from below, and brought them then to the surface, yeah? So these are such things which we are like to try to figure out. So if we are going to Yamuna Creek, that is now not important for the ES203 tests or examination, but I will tell you this again at Yamuna Creek. At Yamuna Creek, you have also, you find together gabbros with tonalites and with diorites. So and now the question is, how can it be that this gabbro occurs together with the tonalites and the diorites? First of all, I mean you can fractionate like this one, such a tonalite from a gabbro. Yeah, but a gabbro has much less silica inside, yeah? So that means, and I mean these gabbros at Yamuna Creek, they are 46 million years old, or 47 million years old, something like this, and the tonalites are 36 to 37 million years old. So, and then the question is how you can fractionate this tonalite from the gabbro. So that means we must produce somewhere a residue, yeah? I mean, if you are going back to the Archean, the whole African continent consists of a lot of tonalites. So there must be then somewhere a residue. So and people are thinking that the residue is then an eclogite, yeah? So in thermodynamically and from a mass balance approach, it is possible that you get that you can have an E chloride as a residual from such a mineral reaction, yeah? Because one can observe this in nature a couple of times, like in South Africa. So, but here I have the problem, I cannot find the E chlorides. I mean, it could be that the E chlorides are still sitting in a depth of, I don't know, in a depth of maybe 30 kilometers, yeah? Or you can make the whole thing by anastasis of a gabbro. That means the gabbro becomes hydrated and transformed into an amphibolite at the lower part, yeah? So, and that means an amphibolite, that is not a problem. You can make an amphibolite out of a gabbro. Then you have there a amphibolite facies source. Afterwards, you heat this up by a later Barthes event. Then the amphibolite becomes dehydrated, and then you can also form an echolite. You can then form a tonalite out of this echolite. Yeah? So, and that is always the game what's going on, and there are some other examples, but what you should know now as an ES203 student, partial melting, you are producing some melt, and then you have also the residual somewhere, and the residual somewhere sitting on the bottom, yeah? So, and for example, if I'm talking about these possible echlorides here in Fiji, we cannot collect them at the surface, because if they are existing, then they are yeah? I do not know this by now. I can just do calculation and assume it or not. So, but if they are existing, then one has to use, or one can also use geophysical methods. So, because the S wave and the P wave in an echloride is quite different from those of a metal rock, yeah? Because till this echloride becomes brought up to the Earth's surface, it will take a couple of million years, if it not longer, and I will physically not be able to collect them anymore. So that is this relationship between the basalts, what we are producing here at the top, and the lersolites, yeah? So, and I mean the scarlet lersolites and olivine nodules and harzburgites, you can then find here in the mantle slag, yeah? That is the mantle slag, that is the oceanic crust. So now we are going to the next slide. So, okay, that is actually the same picture as I have drawn here, but here it's just more professional, and it would be much better if we have got this melt source here. So, but anyway, we have here the ocean, yeah, here is the ocean, the continent. So, and then we have here the different lersolites, the different residual melt, what we are producing here, yeah? So here at the top from the mantle slag, yeah, I mean the oceanic crust is even more at the top, yeah? But beneath you are the first lersolites which you are finding. These are the low pressure lersolites, and the low pressure lersolites, these are the plagioclase lersolites, yeah? So beneath this plagioclase lersolite, you will find the next step, and these are the lersolites which you can find in coral. These are the spinel lersolites, yeah? They are stable at higher pressures. They are stable at pressures up to 90 kilometers, yeah? 90 kilometers, that is a pressure of about 30 kilobars, something like this, yeah? So in beneath, you will then find the garnet lersolites, yeah? So then we have here another description. We have here the fertile peridotites. I mean, all these are lersolite, all these lersolites are peridotites, and here we have the depleted peridotites. So the depleted peridotites, these are peridotites which contains much less incompatible elements compared to the fertile lersolite. So, and you know by now as well what are incompatible elements. These are, for example, the potassium group elements. Yeah, if you are talking about a lersolite, then it's the potassium group elements. Yeah, these are incompatible. I mean, if you are talking about the granite, then they are compatible. Yeah, because the potassium, that is a very common element in granites, but here they are very incompatible. And all the rare earth elements, yeah? The rare earth elements, these are the light rare earth elements, the high field strength elements, and the heavy rare earth elements. So, next slide. No slide longer there, or what? Is this one the next one? This one we have already done, but then we are doing it anymore, once time more. Here you have the phase diagram from the MSH subsystem of the Harzburgites, yeah, in olivine normative rocks. That means we have here again the enstatite, the forsterite, andophyllite forsterite, talc forsterite, antigorite forsterite, leucite, antigorite, and the chrysotile. So, and I told you, if metamorphism should take place, you are producing here this enstatite and forsterite. Then we have the infiltration through cracks here everywhere in the oceanic crust and the mantle slab. These cracks can be deep as 80 kilometers, something like this. So, and then we will hydrate them. So on the way towards to the continental crust, we will hydrate these cracks, and afterwards we will dehydrate them. And that is the way how metamorphism takes place. So I will not spend now more time on this diagram because we have already discussed it. So now we have the MSH assemblage system or suggestion. You know this by now as well, because you have done it in the practical, and I have also showed you in the class. If you are taking the MSH triangle, and you are projecting all the minerals which you have plotted into the ternary MSH triangle, and you are plotting them on the binary line between magnesium oxide and silica oxide, then the bubbles, or not the bubbles, then these different minerals will plot somewhere like this, and then you can just use your hand method, and then you can write down the mineral reactions. You can just try it for yourself because you have done it before. Next slide. These are again the stable aluminous phases in the lersolites. We have done this also before. We have here the plagioclase lersolite, the spinel lersolite, and the garnet lersolite. Yeah, this is the subdivision from the lersolite, and we will do it again when we are talking next, after the midterm break, about the metamorphic rocks, and therefore we will also talk about metamorphism of the ultramafic rocks. So here in these red fields, here we have the pyrolite, yeah? So in the pyrolite is that is everywhere pyrolite. Beneath the mantle slab, that's everywhere pyrolite. And the pyrolite, that is a model composition which was introduced by Ringwood in 1967. And the pyrolite is chemically very identical with the lersolite. So next slide. So and then we have this, and then we have all these components there we have here the oceanic crust. We have here the oceanic crust. Here we have the mantle slab beneath. So in this oceanic crust contains of different gabbros and basalts, but also harzburgites and so on. So now we have hydrated them. We have hydrated them, and now we are sending them the whole sequence just down the subduction zone. So and then we transform these rocks by diffusion processes into metamorphic rocks. Yeah, we did this also before because that is the rock cycle. So and then we are producing different metamorphic rocks, and these metamorphic rocks can be subdivided into different or classified into different groups. And you have also done this again in the practical by using this diagram. Yeah. So in the typical metamorphic facies diagram regarding or according from Escoda in 1915, that is this one. So when the typical metamorphic rock has always a basalt or a gabbro as a protolite. Yeah. You can also have, you can also have eclogite facies rock. Yeah, an eclogite or a blue schist facies rock. That is a rock which can have then also a sediment as a protolite, but it does not look like as a typical eclogite form from a basalt as a protolite or gabbro. So there, if we are talking about the subgreen schist, a subgreen schist that is formed at very low temperatures and pressures, yeah, from a hydrated oceanic crust that is then formed maybe somewhere here, yeah. Here we have a very low pressure and temperature conditions. So if we are if we are increasing the pressure and the temperatures, then we are making a green schist out of it, later an amphibolite, later a granulite. That is then typical for a continental collision zone. Yeah? The continental collision zone is a little bit more hot, or quite more hot, compared to the subduction. I mean, here we have the subduction model that has in a PD pass something like this. Then we are making a subgreen schist, then a blue schist, and then an eclogite. Whereas if we are making a PD pass like this, then this is typical for a continent-continent collision zone, yeah, where we have involved also some oceanic crust. So, and these are the different facies, and I mean the green schist is green because of which mineral in a typical green schist, not in the green schist facies rock, in the green schist. What is the mineral? Which makes the green schist green? Yeah, that's the chloride. Yeah. So, and which mineral makes the blue schist blue? Yes. So, and which mineral will never occur in an eclogite? That is the plagioclase. So the eclogite has actually only two rock-forming minerals, and that is the garnet and the omphacite. And the omphacite is a special variety from a clinopyroxene. Yeah? So, and then we have the granulites, and the granulites can be subdivided in 1 pyroxene granulites and 2 pyroxene granulites. The 1 pyroxene granulites are formed at higher pressures, and the 2-pyroxene granulite, that is the granulite consisting of orthopyroxene and clinopyroxene, is formed at higher temperatures, whereas the 1-pyroxene granulite, which contains the only clinopyroxene, is formed at higher pressures. Yeah? So, and what happens especially here in the transition zone from the amphibolite to the granulite? Yes, increasing temperature, but what will cause, what effect will you figure out by increasing the temperature? What happens there? I mean, of course, you are increasing the temperature, and then something happens to your amphibolite. So what type is an amphibolite is called an amphibolite because they are the rock form in mineral, and an amphibolite is amphiboles, yeah? Therefore it is called an amphibolite. So when the Neil has done all the chemical composition from the amphiboles with you on the board, yeah? So and I mean, if you are looking at the chemical composition, what is different to most other silicate minerals? They contain an OH group, yeah, like the micas, or like the chlorides. So, and what will then happen in the transition zone between the amphibolite and the granulite? It will dehydrate. So it will dehydrate, that means the water becomes removed from the amphibolite, and if you have dehydration, what happens then to your rock? It will melt. So therefore in a granulite you cannot find any schistosity, yeah? Because it is just a molten rock which has recrystallized. So and then you have the melt, and the melt becomes then also removed from the rock. So if you are going this path here now, if you are just going here, increasing the pressure here, in an amphibolite, we are going not from here to here, due to some geotectonic features, you are going from here to here. So then your amphibolite will also dehydrate. So and then you are producing melt. So when this melt becomes removed, and that will then form your tonalite. So in the residuum which is left, that is the eclogite, yeah? That is just that what I have told you before of one possibility how the Fijian tonalites has been formed, yeah? But that is only out of a lot of possibilities, and I'm just working right now on this, and I'm looking for the eclogite, yeah? Because I love eclogites. So and therefore I will find one. So next slide. So then the melt condition of a rock strongly depends on the water concentration inside, yeah? Here you have the system for granites. So and for a granite, you can have a dry granite and you can have a wet granite. So what mineral you can find in the granite which makes the granite wet? I mean, you can have at first, at the beginning, a melt which contains a lot of water, yeah? So, and this granite is then formed at lower pressures, formed at lower temperatures, and this will cause that this granite will not rise up that far to the Earth's surface, because due to the low pressure, low temperatures, this granite will become stuck in more deeper crustal levels, yeah, because it is wet. So, and which mineral or where can you find in this granite a sign that this was originally wet granite? So, which hydrous minerals do you have in a granite? No quartz, there is no water inside. No OH group. I mean, there is a little bit of OH inside in PBN water, yeah? And of course, yeah, that you have also in the plenty place and in the Feldspar, yes, but I mean, we are looking now for a mineral which is typical for a granite where it has a lot, where you have an OH2 group. So which one is this? Which black sheet mineral you can find in the granite? So I mean, I'm talking about these black minerals here, yeah? That is a granite here. So in which black sheet mineral you can find in the granite? Biotite, yeah. So that's the biotite, and if you have a biotite in such a hand specimen of a granite, then there are a lot of them, yeah. Then you know the melt was before wet, and this melt was then not a very hot melt, yeah, because a very wet melt that decreased the temperature. So this granite was then formed maybe at a temperature, let us say, between 600 and 700 degrees Celsius, yeah? Therefore, you don't have to do any microprobe analysis or other chemical analysis. You can just observe this in the field, yeah? So and then what is another sign for a very wet granite, yeah? So do you see the wet granite, the crystals are showing a bigger grain size or a smaller grain size? It's a bigger grain size, yeah? And why do you think granite which was formed by a very wet melt has then a bigger grain size compared to those often formed by a dry melt? Yes, it cools slowly because it becomes stuck in deeper level. So if we are going now to a dry granite, to a dry melt, yeah, here we have always the liquidus and the solidus, yeah. You know by now as well what the liquidus is and what the solidus is. So, and if we have a dry melt, then we have much less hydrous minerals inside, yeah, and the grain size is smaller because due to the fact that you have a dry and hot melt, the melt can rise up much more close to the Earth's surface, yeah. So therefore, the ore deposits, but we are doing this next year in ES203, when I'm still here, yeah, that is depends now very strongly depending here, yeah. If I'm still here, then I will do this with you, because those granites which have been in place very close to the Earth surface, they are forming other ore deposits as those granites which has been formed in a more deeper crustal level, yeah? So, and the same for the basalt system, yeah? We have here the dry solidus, the wet solidus, yeah? So, in the basalt crystallize at higher temperatures, yeah? I mean, that is also a thing what you know by now. A basalt is mafic, and mafic rocks are formed at higher temperatures compared to felsic rocks, yeah? So, next slide, please. So here we have now a triangle diagram showing the eutectic point, which we have showed you here in class and in the practical in these melt diagrams, yeah? That is the eutectic point. So in class we showed it to you, and also in the practical we showed it to you in such a thing, yeah? In 2 dimension. So just simply, yeah, you remember this. So here we have phase X, and here we have phase Y, and here you have the eutectic point. So in there at the eutectic point we are talking about congruent melting, but that is now not the top for this class here. But here we have the eutectic point. So and there we have a melt. It crystallizes and it goes from this direction down here, yeah? So and here we have 3 components and here we have a 2-component system, X and Y, yeah? That is just a binary system, yeah? So but here we have now 3 components. We have quartz, we have albite, and we have K-feldspar. So, and we have a certain chemical composition at the beginning, and here we have the pressures, yeah? And that is the water pressure. So, and then your melt crystallizes and goes down here and goes down. I mean, when I'm saying it goes down, that is a temperature effect, yeah? So it cools down the melt, so and at a certain point, due to their chemical original composition from the melt, then this melt will meet at one point, here at the eutectic point, and then you are crystallize a mineral or minerals of a certain composition there, yeah? So that is just this what you have done in class and in the practical here. Here we have it just in 3 dimensions, that's all. So next slide. Finish, great. So then we will just continue on the board, yeah? So, then we will continue on the board with another funny thing. So there, Neil will then do after the midterm break a practical with you about these things. So now we are drawing two qualitative phase diagrams. You will draw them, I will draw it, and you have to think about it, yeah? So I gave you, I think 2 weeks ago or something like this, we discussed about a phase diagram of water and some other phase diagrams, yeah? And, there we will now continue. So, the phase diagram of water, I will just put it again on the board. But you will remember it, I hope at least. So the phase diagram of water. So, I made it something like this, yeah? So here we have the temperature in degrees Celsius. So, and here we have the pressure, and here we have one bar, yeah? We are making just atmospheric pressure. So then we have this line here. And then you know what's happened with water at very deep temperatures, beneath 0 degree, what you have there, ice, yeah? So above 0 degree, you have water, and above 100 degrees Celsius, you have steam, yeah? So, and that is actually a very simple phase diagram. Which looks like this, yeah. So, then we have here the anomaly of water that is at 4 degrees Celsius. Here we have 0 degree, that is the freezing point. So, and then we have here 100 degrees Celsius, that is there where we are producing melt, yeah? So, and then we have here the critical point. And that is at what? That is at about 370 degrees Celsius, yeah? There we are making out of our water or steam, we are making then a fluid, yeah? So, and then I introduced the entropy, the volume, the density, the temperature, and all these different things. How it will affect your conditions. I mean, if you are increasing the temperature, then you will go from solid, yeah, that is S, to L, that is liquid, to G, that is gas. So, and where do we have in this diagram then solid, liquid, and gas? That is now very easy, yeah? Yes, here we have solid, then we have liquid, then we have gas, yeah? So, but now we are checking what's going on with the entropy. I told you, when we are increasing the temperature, then the entropy will increase as well. Entropy. So now we are looking which condition has then the smallest entropy. That is ice, yeah? So in entropy we are making always an S, that stands for entropy, and then we are making here SS. So when the entropy is then smaller compared to the entropy from what? liquid. So, and it is much smaller compared to the entropy from gas. So that was now a very easy thing, yeah? So, but that is very important in thermodynamics. So now we are checking what's happened to the volume. The volume, we are making always a V for volume. So which of the three phases has the smallest volume and which one has the biggest volume? The smallest volume of all the three phases. Think about the water anomaly. There's something special with water, and think about why the Titanic, you know the Titanic, this big ship which sank in 1912. Why it was sunk? There was an iceberg, yeah. So and then the ship sank, yeah. So, but if the volume from ice would now be the smallest one, then all the passengers of Titanic would have been survived. Because ice is swimming in water. So that is the anomaly of water. No other mineral has this. It has only ice, yeah? And that was unluck for these people at this time that I was not on board, because otherwise I would told the captain, hey, be carefully, there are icebergs, yeah? But the captain has never done a class with me, and so he was just running inside the fucking iceberg. I mean, here in Fiji, you must not be that afraid about icebergs, yeah? But if you are going to New Zealand, you can have them there, yeah? Because they are swimming up from Antarctica to New Zealand, and they have their quite a lot of problem, you know, but they are just swimming there around, yeah? I mean, nowadays, through the climate change, the icebergs becoming always smaller and smaller. But anyway, they are still swimming, a lot of them are swimming around. So that means the volume from liquid is the smallest one, yeah? So, and that is smaller than the volume from solid. So, and of course, this is then much more smaller than the volume from ice. From gas, sorry for that, yeah? So, and that is the anomaly of water, yeah? So, but you can draw this just down again in your exercise, yeah? So now we are going to the next qualitative phase diagram, and with this phase diagram, so and calculate the calculation that is according to the Clausius-Clapeyron. Yeah, then we are introducing now also the Clausius-Clapeyron. So that was, I think, according to the name Clausius-Clapeyron, maybe it was a French guy, I don't know. It is not that important. That is a very from Clapeyron. So, and he introduced following equation. There we have, that is an integral. So, and you had mass in school, and there you have done in mass also the analysis, yeah? I mean the integral and the differential, yeah? So that is actually a very simple integral and differential equation. I mean, it's a lot of work, but it's just for straight lines, yeah? So these are actually like, very formally in school they have introduced you that just a straight line in a xy diagram can be described by y is mx plus b. Later on they have made a function out of it. F of x is mx plus b. So and now we are just using different chemical parameters and replace x with a different chemical parameter. That is just we are using instead of x then the temperature or the pressure. Yeah. So if you have then the temperature, then you can calculate B and the temp, and then that is then the pressure. So, but Neil will do this equation then with you after the midterm semester break. So then we have the integral from the pressure divided by the integral from the temperature. So, and if you are looking for this, then we have here the delta S. The delta S, that is the entropy, divided by the delta V, and that is the volume. So, and there you can then calculate a simple phase diagram, only that you get an idea, because I mean, to calculate a simple phase diagram is, you know, by you just using a pen and a sheet, is still a lot of calculation work. So, but normally you are using for that just computer programs. But you should understand what the computer program is doing. Because otherwise, you will not be able to distinguish what is a good calculation from those what are bad calculations. So, and therefore we will now go back to the phase diagram, not longer of water. We will then use some minerals of Al2SiO5. So, and the Al2SiO5 minerals, this is the kyanite. Then we have the sillimanite. Then we have the andalusite. So, in these minerals, they are all three of them are polymorph minerals. That means they have all the same chemical composition. So, but they have different densities, yeah? A density of kyanite is 3.65. The density of sillimanite is 3.20. So, in the density of andalusite, that is 3.15. So, and now we are making a pressure and temperature diagram that looks for these three guys like this, yeah. Here we have the pressure in kilobar. Here we have, let us say, make it so. Pressure in kilobar. So, and here we have the temperature in degrees Celsius. So, the diagram looks like this. So, and now we are making again the estimation of the entropy. So, which of the three minerals do you think has the smallest entropy? If you are just looking for the densities, then just tell me which mineral has the smallest entropy, and in which field of the three phase fields this mineral will plot. No. Which mineral has the smallest entropy? Kyanite, yeah. So because kyanite has the highest density, so and all of them are Al2SiO5, yeah, they are just crystallographic different, yeah. So the kyanite has the highest density. What is then with the volume with the kyanite? It's the smallest, yeah. So and then the kyanite must be sitting in which of the three fields? Here, here, or there? Yes, here is the kyanite, yeah. That is the kyanite with the density of 3.65, yeah. So because due to the highest density, it has the smallest volume, and the volume that is depending on the pressure, yeah. So and then due to the volume, it is depending on the smallest pressure. Then the kyanite is sitting here on the high pressure side, and if it is sitting here in this diagram on the high pressure side, then we are sitting on the low temperature side, and then the entropy is the smallest one, yeah? So then we have the entropy from kyanite is smaller, and the volume from kyanite is also smaller. So, and which one has then the next so which one do you think has then the highest entropy? That's the sillimanite, because here we are sitting on the high temperature side. .2. So because the andalusite has the smallest one, because it's on the low pressure side. So and then we have here the remaining one, and that is the andalusite, and that is then 3.15. So now we have to figure this out. The volume from sillimanite is then the biggest one, yeah? Then we have here the volume from andalusite. Then we have to check the entropy, and for the entropy is the same. Volume andalusite, entropy andalusite. And here we have the entropy of the sillimanite, yeah? So and then we have here another feature. Here we have the invariant point. Here we have a univariant line. And here we have a divariant field. So, and that can now be calculated using the phase rule. Using the phase rule, that is a rule which they have introduced from the combinatoric. Now I have it at first to find it. So that's the phase rule after chips. The phase rule after chips, that was also a scientist in 1906. Yep. So, and that says F plus P is C plus 2. So, and we are interested in F, and F is then C plus P minus 2. So now we have to think about what the different letters meaning. So P that is the number of phases. So in the, I mean, how many phases do you have in this diagram? Yeah, you have chemically only one. Then you have C, that is the number of the components. So in the components, that is this one. How many components do you have? 3, yeah. So, and then you have the next one. That is F. So, and what means now F? F, that is the degree of possibilities. So what means this? So at the invariant point, yeah, you have one temperature, and to this single temperature, you have only one pressure that is fixed. So that means F is then 0. So if we are talking about the univariant line, then you can go around this line or this line. It depends if you are making a function f of t, that means f of the temperature, or you are making a function of the pressure, that is then f of the pressure. Then you have one possibility. You are getting always a certain temperature to a certain pressure. So, and if you are looking here for the univariant line, you can just get around there, then you have two possibilities, yeah? And that one can calculate. That is then the Schweinemakers rule. So yeah, then I'm actually done for today. So he will do after the midterm break this calculation, and I will do after the midterm break the Schweinemakers analysis, and then we are going to the metamorphic petrology, and with this one we will be busy till the end of the semester.